Hey everyone, my name is Shreyash Sahare and I'm excited to walk you through my Capstone Project presentation for this semester. So this project was completed in collaboration with Parlay Finance and the mentor for this project was James Joe. So here's a quick overview of what I'm going through this presentation today. I'll start by introducing the problem statement first, how we tackle the problem. We move into how we generated the data and prepare the data set, walk you through our loan eligibility framework, followed by a modeling approach, the challenges faced, the results, and contributions. Then I'll also highlight the technologies that I learned and ending with some reflections on the interesting area that I explored while scouring through the project. Coming to the problem statement, the usual traditional US loan system involves like multiple models for each loan type, leading to inefficiencies and inconsistencies. So our goal for this project was to create a single multi-label machine learning model that classifies businesses for different SBA loan types such as 7A, 504, 8A, and 7A Express loan. The model should understand applicant fit using applicant data and business health metrics, allowing us to generate fast, accurate, and scalable decisions. Since real-world loan data wasn't publicly accessible to us due to privacy concerns, we had to generate synthetic data, but we were able to generate around 200,000 plus records of synthetic data, which we adhered a lot, which we adhered with according to the loan eligibility function, which I'll come to later. So this dataset includes around 46 parameters such as revenue trends, credit scores, amount and debt, loan amount and debt. So as I said earlier, we applied realistic financial constraints. For example, the DSCR values were limited to a range between 0 to 2.5 to reflect plausible loan scenarios. So this foundation allowed us for diverse and robust model training. We coming to the loan eligibility function that I was talking about, that I mentioned previously. We implemented a rule-based function to simulate SBA loan eligibility logic. So basically, each SBA program has specific requirements, such as the DSCR values have to be like more than 1.15. The personal credit scores has have to be like greater than 680, and so on. For valid loan purposes, obviously. And this function was this function basically classified businesses into one or more eligible loan criterias or marked them as ineligible, providing the target labels for supervised learning models. Now, before we actually started modeling, we analyzed the relationships between numerical features first because that was of high importance, because that's how we got to know our data better. So we observed strong positive correlations between revenue and DSCR, and also between revenue and NOI, which kind of makes sense because the healthier the revenue is, it often leads to better financial ratios. Interestingly, personal and business credit scores were weakly correlated, showing that these two metrics independently influence eligibility decisions. Now, one of the major challenges that we faced while doing this project was class imbalance, because some of the SBA categories, such as the express loans or the 8A loans, were heavily underrepresented. So we addressed all of them by providing a cap to all the classes at 15,000 samples, and to prevent imbalance. And this was achieved by applying the SMOTE technique for numerical oversampling, while for categorical features, we used random oversampling to ensure balanced representation, which um, which ensured that the data was balanced. The it would improve model generalization, and it would also account for the rare loan types. Now, with the data set being balanced and labeled, we move on to model training. So our focus was on comparing different algorithms for multi-label classifications. So here we experimented with four main models, which included neural networks, XGBoost, LightGBM, and TabTransformer. Now each one had its own strengths. The neural network offered flexibility and performed well on general patterns, although it showed a little bit overfitting. Coming to XGBoost model, it stood out for speed and precision, and we tuned the parameters like learning rate, depth, and gamma for stability using grid search. We also used LightGBM model, which turned out to be one of the best overall model, and it trained quickly, handled skewed features well, and it also had a great accuracy of 88% via with minimal overfitting. Coming to the tab transformer model, it was particularly strong in handling categorical data and generalizing across varied business types. We also tried Praneeth and Gagan actually tried ensemble models, which which involves stacking of several models that produced a high accuracy of 99%, but that obviously reveals signs of overfitting. So weighted averaging was more stable, but had a lower performance at 83% accuracy. So overall, according according to all the research that till now, Light GBM gave us the best trade-off between accuracy, interpretability, and generalization. So we faced several challenges throughout the project. As I mentioned before, we faced the challenge of class imbalance, which we deal with a smooth and random oversampling techniques. But we also faced the synthetic data the synthetic data problem, or the real world data problem, where we had to create synthetic data, and it often lacked the real world edge case variability, making real world generalization tricky. Also, the multi-label logic added complexity because some of the applicants qualified for multiple loans. Feature engineering had to account for domain constraints, and tuning hyperparameters was computationally intensive, and it also required a lot of hyperparameter tuning. So these are my contributions in this project. And some of the areas that I contributed for. So first one would be I worked on generating synthetic loan application data using prompt-based simulations. I used ChatGPT for this. Secondly, I also designed the rule. I also helped in designing the rule-based logic used for the SBA loan eligibility, which powered the label creation. Uh, I also contributed in handling data pre-processing, including feature encoding and standardization. I conducted explanatory analysis on my part using different metrics such as mutual information scores, and Pearson correlation. I also trained and evaluated few models such as XGBoost and Random Forest. And these are some of my learnings, the technologies that I learned throughout the project. XGBoost was a key model due to its accuracy and speed, and I also spent a lot of time tuning its hyperparameters, so I got to learn a lot through that. Smooth was also one of the techniques that I learned through this project, and also the concept of mutual information for analyzing data and performing exploratory data analysis. Also, working on this project often did actually expose me and give me a lot of exposure to the US loan systems, especially the SBA, the Small Business Administration programs that gave me an insight into how financial regulations and lending eligibility are determined. I also explored how financial risk is evaluated using metrics, as I mentioned before, such as DSCR, liquidity, and credit scores. I also saw the challenges of deploying AI and ML in regulated financial systems where accuracy alone isn't enough, but the explainability of model is also quite critical. Last but not the least, using prompt engineering to simulate diverse loan scenarios was a creative way to overcome the lack of real world data. Thank you.